So let's start with our first topic, which is the definition of STA. So STA is a method of verifying timing performance of the design. And you do it using static methods. What are static methods we'll talk about. Can the same analysis be done using other methods, like using simulation, either spice simulation or functional simulation? Yes, it can be done, but it's not exhaustive. So let's understand various features of STA. STA is static in nature. What is the meaning of static is it does not run dynamic simulation. It does not dependent upon test benches or test vectors. So because of that, it can be fast and can run on large capacity designs. It's exhaustive. It uses mathematical techniques instead of input vectors. So required timing checks are performed on all possible paths and scenarios. So it's exhaustive in nature. It does not verify the functionality of the design. For verifying the functionality of the design, you need test benches, simulation, formal verification, equivalence checking. But static timing analysis does not verify the functionality of the design. It's conservative, it's pessimistic and conservative. So to ensure there is a definite guard band for the design time requirement. And so basically you can sign off. Static timing analysis only works for synchronous designs only. It does not work for asynchronous clock domains. And there are specific tools which verifies CDC aspect or clock domain crossing aspect. We have a separate webinar that covers those aspects. So what are inputs to the STA? Inputs to the STA is your netlist. It is the gate level netlist, which has a design representation. Your SDC or input constraint file will be going into details of input constraint file and SDC concepts in second part of this webinar. And logic libraries. Libraries contain your information about your standard cells, gates, what are the delays of those gates, what are the transition time of those gates, that information. So at a high level, these are the various inputs required. Netlist is the design representation, constraints, it tells you what you want to time against, and logical libraries have, as in basically you are mapping to silicon libraries and gates or gates in a particular technologies. It has information about delays of those cells, what are the transition times of those cells, all that information is present in the logical library. So we have understood what is the meaning of STA. Let's understand one of the most basic aspect of STA is what is known as timing paths. So in order to do analysis on full design, STA breaks down the design into smaller portions and which is known as timing paths. What a STA breaks the logic either on ports or sequential elements. So it breaks down the whole design into smaller elements and it breaks the paths, breaks the design at ports and sequential elements. Let's understand this using a particular example. Okay. So let's say you have this design. This design has input port, some combinational logic, then flops, then another set of combinational logic, some other flop, output port, there is clock feeding to the flops. So how does this, how this design is broken down by a static timing analysis tool is, it will break down this design, as we said, on ports and sequential elements. So ports, this is one port, sequential element, and port, this port. So it will break down the design into these. So how will it break down? Let's understand. So it will create timing paths. Okay. So basically it will break down the design into from here to here is one path. So broken down at port and then sequential element, one path. So this is another port to port path. So design broken down into this port to this port. Then this sequential element to this sequential element is another path. Then this sequential element to output port. So basically the whole logic of design logic is broken down into smaller parts known as timing paths. And timing paths are basically either from flop to flop or port to flop or flop to output port. And then timing analysis is performed on each of these timing paths, which are smaller components of the design. Now let's move to our next topic. We have understood what are timing paths. Let's understand what are the various components of a timing path. So the multiple components are start point, end point, and combinational logic. Let's understand these components in more detail. So start point is where data is launched by clock edge, or where data must be available at a specific time. Usually this is input port or register clock pin. Let's understand using the example we were using earlier. So let's say you have this path, this particular path. Here the start point is this input port. On this input port, data is available at a certain time. So that's why this is a start point. So typically start point is input port or clock pin. There are other components also in this design. Let's understand what are the start points of those. So there is this path from the input port to the D pin. Here again, the start point is your input port. There is this path from sequential to the D pin of the next flop. Here, the start point is clock pin. As we said, start points are typically input ports or clock pin. So for this particular path, start point is clock pin. Why clock pin is used as a start point? Because you have to take into account the clock to Q pin delay as well while doing timing analysis. So clock pins are usually start points of the path. There is another path here from this sequential to the output port, and the start point for this is this clock pin. There is another path from input port to the output port, and the start point for this is input port. So start points are where either data is being launched or data is available at a certain point of time, certain time, which is input port. So typically start points are input port and or clock pins. Endpoints. So endpoints are where data is captured by clock edge, or where data must be required to be available at a certain specific time. Usually these are output ports or registered data pins. Let's understand using the same examples we were using earlier. So here is this path from input port to this sequential. Here the endpoint is D pin of this flop, as endpoints are either data pins of the flop sequentials or output port. So for this path, the endpoint is this D pin. For this path from input port to this output port, endpoint is this output port. So there are other paths in this design as well. Let's understand for each of these, what are the endpoints. So as we talk, for this path, this D pin is the endpoint, which is sequential. So endpoints are either sequential D pins or output ports. For this path, endpoint is this D pin. For this path, endpoint is this output port. And for this path, endpoint is this output port again. So start points are input port or sequential clock pins. Endpoints are output ports or data pin of sequential. There are some exceptions to these, but this is the thumb rule. Combinational logic or parts of the logic are elements that have no memory or internal state. So basically your AND gates, OR gates, those are combinational logic. Your flops and latches have memory, they are not combinational logic. So let's go back to our example. Here is one combinational logic, it does not have any memory element. There is another combinational logic, it does not have any memory element. And there is another combinational logic. One important thing to understand about combinational logic is that a combination between a set of start point and end point, if combinational logic is present, there can be more than one path. So let's take this example. Let's say this flop is F1 and this is F2. So F1 to F2 have more than one path. One path is path 1, shown in green. Path 2 shown in yellow. So between a pair of sequential elements, or there can be more than one path. More than one path is possible between a pair of sequential elements. As we are seeing here, there are two paths here. Now, because of this, different paths can have different delays. Maybe delay, this is going through just one combinational logic, so delay is lesser here maybe. And this is going to through two combinational logic, maybe delay is more here. Different paths can have different delays. Different paths can have different rise and fall times. So all those kind of things are possible. So if there is combinational logic between two sequential elements, it's possible that there can be more than one path between those two sequential elements. Or sometimes there is only one path. For example, let's say if there was a flop here. Now between F3 to F2, there is only one sequential path. So it's possible there are more than one path. It's possible there are less than one path. Different paths can have different delay. And that is the role combinational logic is. Combinational logic is where there is no memory or state element. All these three parts combine to make multiple components of a timing path: start point, end point, and combinational logic. Now let's revisit our basics of setup and hold check. What does that mean? So setup check means that data should be available at the input of the sequential device sometimes before the clock edge that captures the data. So let's say you have a flop here, and this is data, and let's say this is clock. Oops. Let me draw a better clock. So this data should be available sometime before the clock edge. If it appears close to clock edge, it can cause problems in the design. So what is that sometime? That sometime is defined by your library. Okay, so let's say this sometime is T setup. So data should be available before this. If it arrives after this, it can create problems in your design. So this enforces a max delay on the path. How it enforces a max delay on the path? Because let's say this is being driven by combinational logic. If you have more delay, data will arrive later, and that forces a max delay. This setup time, that is the time before which data should arrive, is dependent upon technology node, whether it's your 65 nanometer or 7 nanometer, or this is the value which is available in the logic library. Logic libraries typically will have a table mentioning, based upon the load and other factors, and what is the kind of flop you are using, that what is the value of T setup for this flop. Okay, and that value has to be used by STA tool for doing the timing analysis. Let's understand it a little bit more using some waveforms. Okay, so setup time means data should arrive before the flop setup time at the deep in of the flop. If it arrives earlier, like it is happening here, this is the clock edge, and data is arriving earlier than required setup time, then it is said that you are meeting setup time. So here, setup time is met if data arrives earlier than flop setup time. If it arrives later or close to clock edge, then it means that you are violating the setup constraint or violating the setup time. Okay, so here, let's say clock edge is here, and data is arriving close to clock edge, so that it's within the setup time window. Then you are violating the setup constraint. So for a setup check, data should be available sometime before the clock edge. What is that time requirement is driven by the value in your flops logical library, which is given as an input to the STA tool. What is a hold check? Hold check means that data should be stable at the input of the device for some time after the clock edge. So let's say you have a flop here, and let's say this is the clock. Data is coming here. So for at least for some time after the clock edge, this data should not change. And this is your hold. What is that sometime is dependent upon technology node, and that value is available on the logic library. It enforces a min delay on the data path. How it enforces a min delay? Let's say you have a flop launching data, and let's say your data is being captured on this clock edge. So let's use a bigger waveform to explain how it forces a min delay. Okay. So let's say you launched this flop launch data here on this edge, and this flop is capturing on this edge. Now, when this flop is capturing, a new data is being launched here. This data should not change the previous value which is being captured. So there has to be some minimum delay so that the previous data is still captured and stays stable. And that is how it enforces a min delay on the data path. So basically next edge of the launch flop should not change the value with previous value which is being captured. And that is what is enforcing it. So there has to be a minimum delay for the next launch clock edge. Okay. So hold check means that after the clock edge, data should be stable at the input of the sequential element. Let's understand this using a waveform as well. So this is your clock edge, and your data should be held stable for some amount of time, which is defined by the logical library. And if data is stable for that amount of time, you are meeting the hold time. So your hold time is being met. But if, let's say this is the clock edge, and if data is not stable for required amount of time as defined by the library, it means you are violating the hold time, or your hold time is being violated. You're not meeting hold time. Now that we have understood basics of setup and hold check definition, let's understand one of the important concept, slack calculation. Slack is an important aspect of every timing report. So let's understand that. So what is slack? Setup slack is the time it's calculated as data required time minus data arrival time. What is data required time? Data required time is the time by which data should have arrived, and data arrival time is the time at which data is arriving. Let's understand this example using a picture. So let's say you have a start point here, and the start point is going through certain logic and then coming to endpoint. Now, when data changes here, there'll be some clock to queue delay, then there'll be some delay through the logic, then there'll be some additional delay through next logic, and so on. And by the time data comes here to the endpoint, there'll be some delay. So all this delay, which is taken by the signal to travel from start point to the endpoint, is known as arrival time. So let's say it starts at 0, it encounters some delay here, some delay some here, some delay here, and it arrives at a certain time. That is your arrival time. One endpoint can have multiple arrival times with respect to the same start point. And that is dependent on how many paths which are there between start point and end point. For example, in this case, there are two paths from start point to end point. One path is this, and one path is this. So there are two paths. And depending upon on which path you are calculating the delay, the arrival time will be different. So one endpoint can have multiple arrival times with respect to the same start point. What is data required time? Okay. Data required time is what is the requirement of the design, that data should arrive before required time. So what is the required time for data to arrive here? This is typically a function of what is the clock frequency and what is basically at what time this data, which clock is launching this data, which clock is capturing data, and what are the frequencies of those clocks. And it's also a function of what is the setup time requirement of the endpoint flop. So what is slack? Slack is the difference between required time and arrival time. So for example, let's say your required time was this is the time scale, and your required time was this. And data takes certain amount of delay and arrives it here. If it arrives earlier than the required time, it is known as positive slack. And that positive slack means that you are meeting timing, that you should have arrived by this time, but you're arriving earlier, so you're meeting time. If slack is 0, you means you're just reaching at the required time. If it is positive, that means you have some margin and your data is arriving earlier. So slack is positive when data arrives earlier than the required time. Now let's say if data arrives later than the required time. So in this case, your data arrives here at this point of time. What it should have reached by this, which is given by the required time. So in that case, slack is negative. Slack is negative when data arrives later than the required time. That means the slack is negative and you are not meeting timing. If slack is negative, that means you're not meeting timing. You need to fix timing, design, whatever you need to do to fix those in order to meet timing. Because if you're not meeting timing, you will not be able to sign off on the design from static timing analysis, and you can have silicon issues. So you need to meet timing, and if slack is negative, you're not meeting timing on that particular path. So we have understood this using pictures. Let's make it more realistic with the design elements. So you have a flop here, which is going through combinational logic, and then basically ending here. There is a clock. Let's say with the period of the clock is T period, the flop has a certain setup time requirement. So what is the time requirement? What will happen in this design is you will launch the data on this clock edge, and you'll capture on this clock edge. Okay. So basically your data should arrive before this clock edge, or before the clock edge. Only then it can be captured. Now we know from the setup time requirement that data actually not only has to arrive before the clock edge, there is a specific time before which it needs to arrive given by your F setup time. So basically data should arrive before F setup time, and that gives you your timing requirement. So this is your required time. Data has to arrive before this. This is your timing requirement. Now, what is the arrival time? What is the actual time data is taking? So actual time is given by your clock to Q delay, T CKQ, then your logical path delay. So data starts here, it encounters clock to Q delay, then it encounters logical delay, and then it arrives. So your arrival time is given by this. So if your arrival time should be less than what is your required time? Your required time is T period minus F setup. and that gives you slack calculation. So your slack calculation is data required time minus your arrival time. Okay. So this is how you calculate the slack. Of course, as in there are other elements also which get involved as the STA tool does the analysis. There'll be thumb delay on the clock path. The clock will have some other properties like jitter. So all those will come into the picture. But basically, conceptually, at a simplest level, this is how you calculate the slack. And if slack is positive, you're meeting timing. If slack is negative, you're not meeting timing and you need to fix that.
So far, we have talked about only setup and hold checks. There are other type of timing paths which are also checked in STA. Let's understand those in more detail. So we have talked about setup checks and hold checks, which happen on data pins and with respect to the clock pins. STA also does other checks. For example, one of the checks is clock gating checks. Clock gating check is done on clock enable pin with respect to the clock pin. Similar to setup and hold time requirement, there's some specific requirement for enable pin when it can change, when it cannot change, and with respect to clock. And these we'll discuss in more detail. But right now, keep in mind that there are some clock gating checks which are also done. These checks are also dependent upon whether it's NAND gate or gate. We'll go into those details in next few slides. In addition to that, there are async pin related checks like reset pin or clear pin or set pins, checks which are done. And these checks are also related to clocks. Basically, the checks ensure when the reset can deassert with respect to clock. And there are specific checks similar to setup and hold, which are done there to maintain the design correctness, timing correctness. In addition to that, designers can also do some specific data to data checks that between two pins there should be only maximum this much skew which can be required. Those also checks can be added by adding specific timing constraints. All these checks, like clock gating related checks, what should be the value, either it's added through constraints or it's present in the logical library. Like setup and hold timing, what should be the requirement is present in the logical library. Similarly, for reset and clear, what should be the minimum checks requirement, value requirement, it's present in the logical library. For data to data checks and clock gating checks, this value is specified using some constraints or specifying some global constraint. So let's understand these checks in more details as we go forward. But it's important to keep in mind, other than basic setup and hold check, there are some other specific checks either provided by the user in form of constraints or also done in STA.
Other than timing related checks, there is another set of checks which are also done by STA known as design rule checks. Let's understand those checks also. So first check in this category is known as slew or transition analysis. Slew is nothing but time taken by a signal when it's rising from 30% of the VDD to 70% of the VDD. That is known as rise slew. And time taken by signal when it's falling from logical level 1 to logical level 0. Time taken from 70% of the VDD to 30% of the VDD is known as fall slew. In STA, there is specific constraint you can specify in order to ensure that these slew values or transition values have maximum and minimum value. So basically, you can tell that to STA that these transition maybe, let's say, can have a maximum value of say X and have a minimum value of Y, and then STA will check all throughout the design that these transition or slew values are being maintained or not. Why this is important? This is important because all your logical cells, logical cells like AND gates, OR gates, flops, are verified to work functionally or timing point of view correctly within a specific transition range only. And in order to ensure that these cells behave reliably, you have to make sure all throughout the design, those transition or slew values are maintained within those ranges. The second category of this check is load analysis. It's basically you can specify what can be minimum and max capacitance on ports, or you can you can specify what can be the maximum fan out load on ports and output pins. This we'll understand in more details when we go into the second half and understand timing constraints. But basically, STA also checks load analysis and min and max capacitance values on ports and nets and fan out loads on ports and output pins. In addition to that, STA also checks clock skew analysis. So slew and skew mean different things, even though as in there is only one letter difference. Slew means transition time, or how much time it takes from signal to go to 0 to 1 or 1 to 0. Typically, it is measured 30% to 70% of the VDD. Skew is difference in delay of the clock at different points. So for example, let's say you have this path, and then there is launch clock, and then there is capture clock. Okay. Now clock will go through this path and arrive here, and capture clock will go through this path and arrive here. There will be a difference in delays at what time the clock arrives. Okay. So for example, launch clock is arriving here while the capture clock is arriving here. So there is a difference in time in which the clock arrives, and this is known as skew. When do you call skew to be positive? Skew is known as positive when the capture clock has more delay. So when capture clock has more delay, it gives you more time. It gives this path to have more required time because your clock edge is shifted, and so that's why it's positive, known as positive skew. The skew can also be negative, and let's say if launch has more delay, then capture. So this edge, this clock will have less delay, and this will be more. So this edge will reach earlier, and here the clock will come later. So in this case, there is negative skew. So skew is nothing but difference in the clock delays, also known as travel time or latency at different points in the path. Typically, it is measured at the launch and capture clocks because that is where the delay calculation is important for timing analysis. In addition to that, you also have pulse width checks. So let's say you have your original clock pulse like this. As clock travels through the path, the clock pulse can change. So maybe rise is happening at this time, the fall actually shrunk, and the high pulse is now this, the low pulse is also now this. So there is a shrinkage in clock. If the shrinkage is below a certain value, which is the case here, then the pulse width violation happens. So pulse width violation is measured in terms of, you specify the tool. This is the minimum pulse width required for a particular clock. And if pulse is lower than that, then the pulse width violation happens. And the question is, how is it possible that you can have shrinkage in the clock pulse? So as we know, right, combinational logic will have delay. So let's say clock is going through, this can be gating or whatever, maybe clock is going through a logic, and rise and fall delays are different. For example, when it goes through rise, there is X delay, and when it goes to fall, there is less different delay. Because of that, when the clock travels through logic, there can be slight shift in clock edges in rise and fall. Okay, so rise may shift by X amount and fall may shift by Y amount. So if that shift is lesser, for example, let's say you have this clock goes here, and rise delay is by some amount and fall delay is lesser. So you will have a pulse which is reducing. If it reduces below a minimum threshold, which is specified using the constraint, you will have pulse width violation. Let's now understand the checks other than setup and hold in more details. So we'll start with checks on async pins. So what are async pins? Async pins typically in the design are reset or clear pin. I'm using clear pin as an example, but it can be set pin as well. So what happens for a clear pin, taking clear pin as an assertion of asynchronous event is asynchronous. It has no relationship with the clock. So basically when you cause this clear to go from 1 to 0, this is known as assertion of clear or assertion of reset. It has no relationship with the clock. Instantaneously or with some delays, you will have output changing to 0 or 1 because of the as per reset value of the clock. Deassertion, what happens? This is during assertion. Now what happens during deassertion? When the deassertion happens, during deassertion, rather than start taking data from here, the flop will start taking data from here because now reset has deasserted. Now, in order to ensure to take data from here, this data is dependent on clock. So when you migrate from asynchronous, so basically migrating from asynchronous to synchronous events. During that time, in order for design to behave reliably, that deassertion is dependent upon clock, and there needs to be some time requirements in order to ensure design is behaving reliably, similar to your setup and hold. So there are timing checks needed to be done to avoid that unknown state if this transition happens very close to the clock. So what are those timing checks? So the first step check is recovery time. Okay. What is recovery time? Is reset, this is the asserted phase, and this is when it's deasserted. This deassertion means signal going, in this case going from 0 to 1, should not happen very close to clock edge. It should happen sometimes before the clock edge, and that time is the recovery time requirement. So your deassertion should happen sometime before the clock edge. That time requirement is given by the logical library of your flop, and this time requirement is known as recovery time, similar to setup time, that at some time before only it can deassert. Assertion can happen at any time. Deassertion should happen sometime before the clock edge, and that is recovery time requirement. If this deassertion happens very close or within this time window, yeah, design is failing a recovery time. So this check is only needed for synchronous, asynchronous pins, not for synchronous pins, because synchronous pins feed through, let's say if you have a synchronous reset, that is fed through D pin only, and that is already covered in your setup and hold time because signal already has a requirement with respect to clock. But for async pin, deassertion is checked separately, and these are checked. When the deassertion can happen with respect to clock, there should be some time before that, and that is recovery time. Now, after this deassertion also cannot happen after the clock edge for some time, again to ensure that the design does not go into an unknown state, and this is known as removal time. So a deassertion cannot happen very close to the clock edge here and very close to the clock edge here. So this window is when your deassertion cannot happen. Before the clock edge is known as recovery, and after the clock edge is known as removal. These values are calculated from your library. So let's understand other kind of check, which is not related to setup and hold, but basically clock getting check. So what is clock getting check? Clock getting check is done on clock gates. Basically, it is done when the signal can control the path of the clock at a cell. So for example, let's say you have AND gate and one of the input is clock, and let's say other is enable. So see, this signal can control the path of the clock, and so clock getting check is done there. In order for clock getting check to happen, the signal must be used as a clock downstream. What is the meaning of it being used as clock downstream? Is it should either feed a flop or a latch clock pin, or feed output port, or feed generated clock. Okay, so for example, let's say you have AND gate and it's feeding clock pin of the flop. That means it is being used as a clock. And this is clock and enable. But if you have AND gate and it is feeding deep in of the flop, that means it's not being used as a clock, and no clock getting check will be done. Of course, unless it's not a generated clock circuit. So requirement is basically for clock getting check to happen at a certain cell, it has to be used as a clock in the fan out. The intention of this check is to ensure that transition at the gating pin does not unnecessarily create an active edge in the clock fan out. Let's understand that using specific cells for which clock getting checks are done. So we'll start with what we call active high clock getting check, which is done on AND gates or NAND gates. Okay. Now, in order to ensure, let's say you have this clock going high here. Let's say clock is going high here, and this is clock, and let's say your enable changes from 0 to 1 in this region. Because of that, output clock will change here, close same time as enable. So it can cause unnecessary edges because enable is changing in a region where clock is high. It can cause active edges to shift. So basically then the requirement is clock should not change, or enable should not change within this region. And not only just in this region, there is an additional buffer which is known as setup and hold. So basically your enable cannot change in this region when it's an AND gate. So when it's active high clock getting cell, and the clock is 1, sometime before this and sometime before after this, your enable cannot change. And this is what is checked in your clock getting checks. So clock getting check will check that enable, during the setup check, it will check that from the clock rising edge, enable should become stable sometime before that. What is that time is defined by constraints or global level constraints or clock getting cell logical library value. It is checked that before the clock edge, for certain set of time, your clock enable signal cannot change. And after the falling clock edge, for a certain set of time, your enable cannot change. If enable changes during that period, your either setup or hold, depending upon when it is changing, is violated and it is reported. So this is for when the cell is AND or NAND. If the cell is OR gate, which is the case here, then during the low value of the clock, sometimes before that and sometimes after that, the clock enable cannot change. And this is what your setup and hold check for clock gating will check. It will check that during this period, your enable cannot change, and if it violates, it will flag a violation. And during this period, your enable cannot change for an OR gate. Now, what happens is sometimes when it's some other cell other than that, then other than NAND or OR controller, then tool will issue a warning that it can't figure out how to do this check, and users can specify what exactly check has to be done using the set clock gating check command. So tool will warn you that it can't figure out, it's a complex cell for me. I cannot figure out whether I should be doing the check in the clock high period or with respect to clock low period. So it cannot figure that out. So you have to tell that using the set clock gating check command. Let's go to our next topic, which is about latch-based timing. And it's an interesting topic and probably not very well understood by everyone. So we'll try to understand it conceptually and with more clarity. In a flop-based design, so far we have seen flop-based designs. Flop-based design, data is launched and captured on clock edges. So basically, let's see, this flop will launch data. This flop will launch data on this clock edge, and the next flop will capture the data on the corresponding clock edge. So data is launched and captured on clock edges, and there is very little flexibility on that it will be captured on clock edges. Now, what happens because of that? Let's say you have an additional flop here, and let's say this logic delay is more, and this logic delay is less. Okay. Now, because of that, because of the edges-based launch and capture, no matter if this delay is more, you still have to meet this time in one clock period. This, again, you have to meet in one clock period. So there is little flexibility in using, let's say if this delay is more, can I use it here? Flop-based design does not provide those flexibilities. Now let's see how it differs from a latch-based design. So latches are not edge-based. They are level sensitive, which means they capture the data either when clock is high or clock is low. So here we have positive level latch. What that means is when the clock changes from 0 to 1, the latch can start capturing the data. This is known as open edge of the clock. And when clock goes from 1 to 0, it closes and does not stop capturing the data. During the period during the time when when latch can capture the data is known as the period where latch is transparent. So it is this is the period where latch is transparent, and it acts like a buffer that whatever comes to deep in goes to the output. Now, in this case, how does latch provide more flexibility than flop? So once the latch opens, it can capture the data here, it can capture the data here, it can capture the data here. So in this case, data actually arrives later than the clock edge, and latch can still capture that data from D to Q pin. If the data arrives earlier, which is the case here, where as soon as the latch opens or clock goes from 0 to 1, it can capture the data. So if data arrives earlier, it behaves as flop was behaving. But if data arrives later, like in this case, which came after the clock edge, it can still capture the data. So latch provides little bit more flexibility in terms of that you need not necessarily have that data arrives before the clock edge. Data can arrive later than clock edge as well, and you can still capture it. Like in this case, deep in changes after clock has gone high, and latch is still able to capture the data. So it provides more flexibility. How that flexibility can be used, we'll understand using one more example. So let's see this case where you have a flop here. It is launching the data. Then the data is captured by a positive level latch. And then there is another flop in the fan out. So let's first see the case where basically your disk delay LD is less and data actually arrives before the clock edge. So here, let's say if data arrives before the clock edge, there is no difference in terms of how latch would behave or flop would behave. And you will latch will open and capture the data at the clock edge, and it will capture the data, and next cycle of the clock will be used for the logic next. So for this data will be captured here, and then next full cycle will be used for the next flop. So if data arrives earlier, there is no difference between how the flop would have behaved or how latch is behaving. So data arrives earlier, this data is captured here, then next full clock cycle is given to the next logic. Now, let's say data arrives later than the clock edge. So data arrives here. If this were a flop, you would have setup timing violation because data is arriving later than the clock edge. It should have arrived sometime before the clock edge. So if this were flop, you would have had a setup time violation. But in case of latch, data arrives later here. So you get this, your data gets on this latch, your data gets captured here. And for the next logic, you get little less than one clock cycle to meet timing. So latch allowed you that flexibility that if this logic delay was more and maybe this logic delay was lesser, you can still meet timing by allowing some data to take some time from there to here and give less than one clock cycle for the next logic. This is known as time borrowing. So what basically you're doing is, rather than forcing the data to arrive before the clock edge and then give one full clock cycle to the next logic, you're taking some amount of time from the next full clock cycle and giving it to the latch to meet timing. So you're borrowing the time from this path and giving it to here so that this particular path can meet timing. And latch provides this flexibility, and this is known as time borrowing. Now, how much time can you borrow? Okay. So time you can, if the data arrived earlier, it behaved like a flop. If data arrived little bit later, but still in the transparent period of the latch, transparent phase of the latch, you could meet timing by borrowing from the next cycle. But if data arrives later than the trans period, which is here, you cannot meet timing because you have missed the window where latch could have captured the data. So the worst case can be data can arrive as late as when the latch closes. It has to arrive earlier than that. If it arrives later than that, then you're not meeting timing. So latch-based design allow this flexibility of time borrowing, and which can be useful in the cases where some part of the logic has more delay and some part of the logic has less delay, and you can borrow time from the next cycle to here to meet latch timing. This flexibility does not exist for flop-based design. So far, we have understood the setup and hold time behavior when single clock or similar type of clocks are present. What happens then? There are multiple clocks in the design with maybe different frequencies of the clocks. So when there are different frequency clocks are present, the setup check is calculated, or the most restrictive setup is identified by first expanding the clock to a common base period. So let's say you have two clocks here, clock A and clock B. STA finds the most restrictive setup, and it finds the most restrictive setup by first expanding the clock into a common base period. So basically an LCM of the period is found and clocks are expanded to that. And in that, whichever is the closest launch and capture, that is used to find the most restrictive setup. The most restrictive launch and capture may be just not dependent upon the period. It may be dependent upon delays as well, but basically most restrictive setup is used. The hold check is dependent upon the setup check. And what are the rules to identify hold check? We'll go into a little bit later in next few slides. But basically two things to remember. Clocks are expanded to the common base period, and based upon that, setup check is identified, and then the hold check is dependent upon setup check, and it is modified as per the setup check. So clocks are expanded to common base period, and in this case, one clock is divided version of another. So you have expanded to common base period. You could have launched the data here, and this data can be captured here, can be captured here, it can be captured here, and it can be captured here. STA uses the most restrictive setup, which is the default setup edge, and that is what is used for timing. Of course, you can make the STA changes from here to here by applying a constraint known as set multi-cycle path, but by default, it will expand the clocks to a common base period and find the most restrictive setup edge. What happens in a hold check? We will talk about that. And this is the example we are going to use to explain hold check. We'll first go into rules, thumb rules, which are used to identify how hold check is identified, and then we'll come back to this example. Now, in terms of setup check, let's understand this example. You're launching the data and you're capturing the data on the negative edge of the clock. So basically you're launching data here and you're capturing data on the negative edge of the clock. So your setup check is basically half clock cycle, which is this. You launch the data here and you capture the data here. Hold check actually turns out to be this. Why? Let's understand. So for hold check, there are two rules which are followed. First rule is data launched by setup launch edge, the setup launch edge which you're launching, must not be captured by the previous capture edge. Okay. So you're launching data here. This is your setup launch edge. This must not be captured by the previous edge. Okay. So data launched at the setup launch edge must not be captured at the previous clock edge. So data launched by setup edge must not be captured by previous setup edge. Let's say, let's check with this data setup edge. So data launched by setup launch edge must not be captured by previous capture edge. So that is one rule. Second rule is data launched by next launch edge must not be captured by setup capture edge. So let's say you're launching data here and capturing here. So next launch edge is this. Data launched by next launch edge must not be captured by current setup capture edge. So two rules. two rules. Data launched by setup launch edge must not be captured by previous. So current setup launch edge must not be captured by previous. Data launched by next launch edge must not be captured by the current capture edge. So let's come back to our half cycle example and understand that. So in this case, this is your setup launch edge and this is your capture. So data launched by setup edge must not be captured by the previous clock edge. So this is your previous edge which was capturing the data. So data launched by setup edge must not be captured by previous clock edge, and this defines your hold check. According to second rule, data launched by next launch edge, which is this, must not be captured by the current capture clock edge, which defines this, which is essentially the same, just one cycle move. So this is why this becomes your hold check. So for when multiple clocks are involved, clocks are expanded to common base period, and then the most restrictive setup is found. And based upon that setup, hold check is calculated. Rules for calculating hold checks are: data launched by setup launch edge must not be captured by the previous capture edge. Data launched by the setup launch edge must not be captured by previous capture edge. And data launched by the next clock edge must not be captured by the current setup capture edge. And these are the two rules used to identify the hold check. And in this particular case, the hold check for a half cycle path comes out to be this. So let's understand a little bit of terminologies related to timing arcs and cell delays before we start looking into setup and hold checks with more details with clocks and other things involved. So one of the important terminology which is used is timing arcs. So there are two types of timing arcs, one known as cell arcs and then second known as net arcs. Cell arcs are nothing but basically what are the input to output connections in the cell. So in STA, when you provide library inputs, logical libraries, each libraries will have arcs, which basically tells that this input is connected to this output. These arcs will have, as in what will be basically the rise and fall time. So basically when input changes at a certain rise, what will be the output changing to, after how much time, what delays it will cause. So basically these are known as cell arcs. These are present in your logical libraries. They have functionality as basically what is the input to output functionality, what is the input to output rise or fall time, what is the input to output delays based upon what load is given and all that. Then there are net arcs. Net arcs are arcs which connect one cell to another cell. And again, for them, basically, there is a way of calculating what is going to be delay on those cell arcs. When data travels from here to here, what will be the rise and fall times? How will they change when you go from here to here? So basically, two types of arcs, cell arcs and net arcs. There are combinational arcs. What is a combinational arc? Combinational arcs are arcs which don't involve any state element. So let's say this NAND gate, your input to output, this is a combinational arc. Your input changes, but there is no state or a memory device here. So input to output, this arc is known as combinational arc, and it is, again, as I mentioned, it is present in your library. That this means this input is connected to this output combinationally, no state element involved. B input is connected to output combinationally, no state element involved. So these are combinational arcs. Then there are sequential arcs. Sequential arcs means they are typically related to clock, like our setup and hold timing. So let's say you have a rising edge clock flop here. Then the D pin is related to clock and basically to the rising edge of the clock. And there is this arc which is saved in the library, which is known as setup arc and is separately a hold arc, which tells you what is the setup and hold time requirement of the library. And since it's related to clock, it's known as sequential arc. Similarly, in a logical library, the clock, when the clock rise edge comes, and to output what is the delay which will occur, is also a sequential arc, and it is defined in logical library with respect to if it's a rising edge clock. With respect to rising edge of the clock, the delay is defined. Plus, basically, it's a function of the load. So based upon the load, the table is created and delay value is defined. Similarly, for async pins like reset or set pins, with respect to clock, a delay or recovery and removal time related values are specified. So these are sequential arc. Your clock to output delay, your recovery and removal related delays, and your setup and hold, which are related to clock, and these are known as sequential arc. There is another term which is used to identify the sense of the arc. What is meaning of the sense of the arc? Sometimes it's important to figure out when the input changes, whether output is going to change in the same direction or in opposite direction. So there is one type of arc or terminology known as positive unit, which means when input rises, output is also going to rise, or when input falls, the output is also going to fall. So these arcs are known as positive unit arcs. They follow the input in the same direction and known as positive unit. Negative unit arcs are which follows the input in opposite direction. So if input rises, output falls, or input falls and output rises. So these arcs are known as negative unit arc. They follow the input in opposite direction. Sometimes input or output may not follow this behavior, that when input changes and goes from 0 to 1, output may rise or output may fall. It's not possible to predict. Then these arcs are known as non-unit arcs. One such example is XOR gate, where when input rises, output can rise or output can fall. Then, and because this can follow in any direction, the arcs are non-unit. So non-unit arcs is when you cannot predict based upon input changes how output is going to rise or fall. So positive unit is when input changes, output follows in the same direction. Negative unit is when input changes, output follows in the opposite direction. And non-unit is when you cannot tell when input changes whether output is going to follow in the same direction or not. So let's understand a few more terminologies. We understood what are timing arcs and timing sense. Let's understand how the cell delays are calculated and what are the models, and some clock network effects. And then we'll revisit setup and hold check in more detail with all these effects into place. So when the cells are present, as we saw, there are cell arcs which are present, and the cell arcs will have delays. So typically, how the delay is calculated is a function of what is the transition on the input or slew on the input, and what is the output load and capacitance. Logical libraries typically will have a table which will have the delay values as a function of input transition and output load, and based upon that, STA tool will calculate the delay depending upon the present netlist on which it's running, what is the load being calculated, and what is the input transition. There are multiple models which exist for computation of cell delays, which we are not going to go into details, but basic thing to understand is it's a function of input transition and output capacitance. And typically delay is measured from input side to the output side based upon slew, how much time it takes when input changes from 10% to 90%, how much time it takes for output to change from the 10% to the 90%, and that is known as the delay or the propagation delay of the cell. And it is a function of input transition and what is the output load or capacitance on that cell. When the clocks are present in the design, okay, and they are connected to their sources, clock will also have buffer, inverters, clock gating, other elements which are part of the clock logic. And this logic will cause some delay in the clock path. For example, I have a circuit here where this clock is connected to a flop here. And this clock is after some inverters connected here. Now, this path and this path, which is the clock path, will definitely have some delay difference. And this delay difference between clock paths is what is known as clock skew. Clock skew is basically the delay difference, or it is also known as latency difference between your launch of the clock and the capture of the clock. And this is typically happens because of the delay element, because the logic present in the clock path. This skew is known as positive skew in this particular case because the capture side delay, assuming capture side delay is more and this is less. So it's a positive clock skew. Positive clock skew can make your setup time meeting little bit easier. So for example, here, if you were launching data here, you had to capture the data by this time. But because of clock skew, this edge is shifted from here to here, and this edge is shifted from here to here. So because of the skew, you get this additional time to meet setup, and that relaxes the setup time a little bit when the case of positive clock skew. The whole check may have different behavior because you might have to now keep the data stable for a longer time because of this skew. So positive clock skew can help sometimes making your timing to meet easier, at least in the setup side. It can also happen that you skew between launch and capture in such a way that launch clock reaches earlier, capture clock reaches earlier, while the launch clock reaches later. So if there were no clock skew involved, you were launching the data here and you're capturing the data here. But now because of clock skew, the capture is reaching earlier. So you have little bit less time window to meet setup. And this is known as negative clock skew, that your capture clock has lesser delay or reaching earlier. So clock network, because of different delays, can impact setup and hold time, and we'll understand those calculations in the next topic. In addition to that, some other terminologies which are involved is, let's say you define a clock at this particular point. From the clock source, which is PLL, and let's say you define a generated clock here, the delay which is used that delay is known as source latency or delay in the source path. From the clock definition point to the flop pin, the delay which is involved is known as network latency. So this is the latency on the clock network path, and this is the latency from the clock source to the clock definition point. In addition to that, there is one more effect which takes place. Clocks are not ideal because of the physics. So ideally, if you're saying you have a clock, you will assume that clock will change, go to rise at t equal to 0, and let's say 10 is the clock period, it will go to rise again at t equal to 10. Practically or realistically, what happens is clocks usually have some jitter. What is the meaning? Jitter is basically there is some uncertainty in the clock edges. So rather than rising edge coming at right at time 0 itself, there is can be slightly, it can come slightly later than at time 0, it can come slightly earlier than time 0. And this is known as clock jitter. It happens on any physical device or a clock generator or a PLL, that you will have some clock jitter. It can come early than ideal time. It can come slightly later than earlier time. And your STA timing tool, because you finally clock can come earlier, has to take this into account as well. So clock jitter is another effect which we need to understand to look into setup and hold timing. So let's understand how STA tool reports setup and hold checks. So we have seen the pictures of the design which we have been looking at. Now, when STA does analysis and reports the timing, it converts first that logic for reporting into what are known as nodes and cells and arcs. So, for example, for STA, this will be a node or a net. This Q pin this Q pin of this clock will be a node. D pin will be a node. Clock pin will be a node, and all the logic from which is connected are converted into arcs. For example, Q pin to A pin of this gate here is an arc. Then there is an internal arc, which is the cell arc. So there's a net arc and cell arc. Similarly, DEX logic is converted into arcs. So basically, STA reports the timing converting this representation to a node and arc-based representation. So Q pin will be a node. This is another pin. D pin will be a node. Clock pin will be a node, and then there'll be arc from one node to another. Then there'll be a cell. There'll be arc from one cell to another, and this is how it will report timing. Here is an example of STA-based timing report. So there is start point. We know what is a start point. It is mentioned here. Then there is end point that is mentioned here. Path group is basically what clocks are timing this path. What is a path type? Max means the path is a setup path, or if it's a min delay path, max means it's a setup check. At the bottom, it will tell you clock edge. What is the delay on the clock network? It says propagated. That means clocks are propagated. So you have two stages in STA. One stage is when the clock tree is not built. In that case, some user specified or constraint specified value is used. After clock tree is built, the delay value which is used is actual delay on the circuit, and then at that point of time, STA says it's a propagated delay. What is the transition time or slew on each of these input as it moves forward? The slew changes because of the load, because of going from input of the cell to the output of the cell. Nodes of the designs are mentioned here. What is the library setup time? What is the clock uncertainty value, either user specified or calculated, is used. And at the bottom, it tells whether timing is met or violated. If your slack is negative, that means you are violating the time, or it's not meeting the time. If slack is positive, you are meeting the time. And this is also shown by showing in bracket slack bracket violated, meaning you're not meeting the timing. If this would have been met and meeting met, that means you're meeting the timing. So this is how typically a setup report looks like. STA converts the design into a node and arc based representation, and each of those nodes are represented in a text report. Start point, end point, all the nodes in the design, what are delays on each of those nodes, how the delay is changing as it is going through, and at the end, whether you are meeting timing or not meeting timing. This we cover in more detail in our STA advanced course, where we use an open source open timer tool to show you how to analyze the reports in detail. Now let's go to second half of our webinar, where we'll go into a little bit more advanced concepts of STA, and we'll also then understand basics of timing constraints and various commands related to SDC or timing constraints. Let's revisit our basic setup check. We had looked into that. Setup check is basically your data should arrive sometime before the clock edge, which is given by your T setup. That is, the data should arrive at the T pin of the flop at least T setup time before the clock edge. What are the multiple elements involved here? There is clock to Q delay when data is launched. This is a sequential arc. There is a clock to Q delay or propagation delay. Then there is a delay on the combinational logic. And then there is a flop setup period, that data flop setup requirement, that data should arrive at least this time between the clock edge. So based upon this, let's calculate what is the maximum delay this path can have. So you have clock to Q delay here, coming from here. Then you have combinational delay here, coming because of this logic here. Clock to Q delay plus combinational delay and the setup time requirement of this flop should be less than the clock period. If it is more than the clock period, you're not meeting timing. So this is our basic setup check, which we revisited. Now let's understand clock network effect, which we had seen. What happens when there is clock skew, which is present? What happens because of the clock skew is your clock was coming here, the clock edge was here, but because of the delay, this part has no delay, and let's say this path has additional T skew delay. Because of that, rather than clock edge coming here, it is arriving time T skew later, and that relaxes your setup timing a bit. So rather than your clock to combinational delay, clock to Q propagation delay, and combinational logic delay, and T setup, rather than being less than equal to clock T period, you get an additional margin, which is clock skew, which is happening because your clock is slightly shifted. Now, skew, as we had seen, skew can be positive or negative. If skew is positive, which is the case here, you will get additional margin to meet your setup time. If skew is negative, your timing becomes more pessimistic because clock now arrives early. So when the skew is present, that equation changes to clock to Q combination propagation delay, combinational delay, and T setup should be less than equal to period plus clock skew. Whether skew is positive or negative, the equation will automatically handle it. We had seen another clock effect, which is clock jitter. And if you remember, clock jitter is nothing but if you have an ideal clock and the rise edge, let's say, comes or fall edges comes at equal to 0, it is not always 0. There is some uncertainty in the clock edge, and that is measured as called as clock jitter or clock uncertainty. Now, because of that, what happens? We are assuming the clock edge to come here. Now, because of the skew, it comes, your clock edge comes here. Now, because of skew, it comes little bit later. But because there is clock uncertainty, the edge can come slightly earlier or edge can come slightly later. To make it pessimistic for setup timing, we make the edge come earlier so that the timing becomes more strict, and our equation changes to clock to Q combinational delay, combinational logic delay, and T setup should be less than equal to T period plus T skew minus setup uncertainty. So the clock uncertainty can be set up, and basically for setup edge, uncertainty and hold edge uncertainty values can be different. So using a value called setup uncertainty, and it makes your setup little bit more pessimistic. Let's revisit. So because of the clock skew, you got additional margin if the skew is positive, and equation automatically takes care of that. But this margin is reduced because the clock edge can come little bit earlier, and that is measured in your clock uncertainty. Now, what happens in the case of hold check? If we revisit our rule for hold check, the rule was that next setup launch edge should not cause current data change. So let's say you launch the data on this flop, then there is a combinational delay. This delay has to be minimum certain value, so as previous data which is being captured is not changed. What is that minimum value? Let's understand. So clock to Q, so there is a delay clock to Q, and this combinational delay, this has to be greater than the whole time of the flop, so as the previous data is not changed till its capture. So clock to Q delay, then the combinational delay has to be greater than hold, and data has to stay stable after this clock edge, which is given by the T hold value. Now, what happens when there is clock skew? In the presence of the clock skew, your edge changes little bit. Rather than your capture clock edge was coming here, and rather than that, it is now coming little bit later. And this, now that means your data has to stay stable for a longer amount of time, and that gets added into your equation. So clock to Q combinational delay and this combinational logic delay should have stayed stable for some amount of time after the clock edge. Now, because of the clock skew, not clock edge changes, and now it has to stay stable for a longer amount of time. So equation changes to clock to Q delay, combinational delay should be greater than T hold plus T skew. Now, if skew is positive, this makes hold pessimistic. If skew is negative, this hold little bit you relax in terms of meeting hold timing. So sometimes during clock tree synthesis, these can be used for your advantages. For paths where setup or hold timing is difficult, you can use this tricks by maybe adding some clock skew to make setup or hold timing meeting easier. Now let's take your uncertainty or jitter into account. So as the jitter can happen in any direction, so you had a clock here, the clock skew was added, but because of the jitter, let's make it pessimistic, you can move the jitter. Jitter can happen on either direction of the clock edge. To make it pessimistic, not only data has to stay stable for greater than hold plus skew, in addition to that, it also needs to take into account the hold uncertainty value. So clock to Q delay and combinational delay should be greater than your hold, T skew, and hold uncertainty value. Okay. So it makes, because the clock edge can shift in any direction, it makes it, STA does it in a pessimistic way, and you have to stay stable for a longer amount of time. So your minimum delay has to be more. Now, as we had seen that path elements have delays. Okay. The delay have certain values. Delay can be more. On the same path, delay, there is some minimum delay value and there is some maximum delay value. Delay can be more or less depending upon whether one data is rising or falling, or basically you can have multiple libraries, different parts of the chip can have different delays, and in order to account to that, you have different libraries like minimum libraries, maximum libraries, and nominal libraries. The basic thing is a path delay is can be have some minimum value, maximum value, and so let's say some nominal value. And while doing STA, for STA to stay pessimistic and make sure no matter how what the actual silicon is, your timing is going to be met. What it is for setup is to make setup pessimistic. It uses maximum delay value on the data path. So basically, to make it worse, data should be launched as late as possible, and then the data path should have maximum delay. So clock should come as late as possible on the launch side, and data path delay is maximum. On the capture side, it's pessimistic when clock comes as early as possible. So let's say you have this clock. This is on the launch side, and this is the clock on the capture side. You make this edge, the capture edge, come as early as possible. If it moves earlier, your setup will become more pessimistic, and that is what STA does. So your launch clock comes as late as possible. The delay on the data path is taken maximum value. Clock comes as late as possible for setup, and capture clock comes as early as possible. And this is how setup check is made more pessimistic and how setup check is done. Now for the hold check, it's a minimum delay equation. So you want launch clock to come as early as possible, data path to use minimum delay, and capture clock to come as late as possible. That makes it more pessimistic. Now, even though this is pessimistic, sometimes there can be undue pessimism because of this. What is undue pessimism? Let's say you have this path, and launch and capture clocks are, clock logic is this. So you're saying for the launch, I will use max delay, basically capture the clock as late as possible. And for capture side, I will use as minimum delay as possible. Now, if the clock logic has some portion which is common, so in this case, this part of the logic is common. Either you can have a delay value of 0.1 on this, on real silicon, or delay value of 0.5 on this. Basically, this part of the logic will always have some delay. And if you're using different delay value for launch and capture, that is pessimistic, but not it's undue pessimism. It's not realistic. So using different delay values for launch and capture can sometimes cause undue pessimism, as in this case, because in reality, clock, whatever chip you're using, clock logic will have certain amount of delay. Either clock path will be taken from here, or the clock path will be taken from here. So this undue pessimism can sometimes be reduced, and there is a technique which is an advanced concept known as CRPR, which reduces clock path pessimism when there is undue pessimism by taking different paths for launch and capture. And this is an advanced concept, but basically you need to understand that there can be undue pessimism because of taking worst case for launch and a different delay for capture. And there are techniques in STA by turning on, and which is now, I think, more default in most of the tools, by adding something called CRPR, which will reduce undue pessimism in the clock path logic. Now let's go into slightly advanced topics of STA. Since this is a basic course webinar, we'll be covering these topics at a high level so that you have a conceptual understanding and aware of these effects. First, let's talk about crosstalk and noise. So what is crosstalk? When there are signals or wires which are present in close proximity of each other, there is something called coupling capacitance. What it means is, if the signal is changing, like here, the nearby signal can also change because of this effect. Okay, so let's say this signal is changing from 0 to 1. This is known as aggressor, which is changing itself. And on the victim, it can cause a change also. Now, if aggressor is changing, let's say from 0 to 1 in the design, and that corresponding signal which is close by, which is known as victim, is also changing in the same direction, it can cause this signal, the victim signal, to change faster. Okay. And because of that, because it changes faster, the delay, the rise time changes, and the delay on the circuit can become lesser. This is the case when both the signals are changing in the same direction. If the signals are changing in opposite direction, as shown here, so this signal is changing from 0 to 1, and this signal is changing from 1 to 0. Because of coupling capacitance, this signal will try to push this signal in the same towards itself. The delay, the change can become slower for this signal, and that can make delay more. The transition can become slower, and that can cause delay to become more. So basically, because of wires running very close to each other, there is a coupling capacitance which is introduced, and depending upon whether signal is changing in the same direction or opposite direction, the delay of the path can change. And STA, while doing static timing analysis, takes into account that these delay changes, also when these delay changes are present, you still have setup and hold and other timing checks being met and not violated. And this is known as crosstalk. So the one effect of the crosstalk is it can impact delays, can make it more or less, and STA needs to take that into account. There can be another situation where this signal is changing while this signal is not changing. Now, because of that coupling capacitance, this signal can have a slight pulse or a glitch which can come up, and that can cause functional failures. So if the signal is not changing, if both signals are changing, it can cause delay to become more or less. But if the signal is not changing at all, it can cause a glitch to be present on the victim. And STA needs to make sure these glitches are not present or below a threshold value. And that is another effect of crosstalk, which can cause glitches. And STA, while doing timing analysis, ensures these glitches are below a threshold value. Modes and other variations which can happen. So when chip is made, right, it's a physical process, and the process can have some variation. You can have variation in the form of one wafer to another wafer, or within the wafer between two A and B dies, you can have variation. What this variation causes is you can have different delays, like manufacturing. Because of manufacturing, you can have a different delay in this. What's this different delay? Or maybe the gates are created slightly differently, which can cause delays, transition times can be different. And STA needs to take that into account, because not only this wafer should work, this wafer should also work, this should work, this should work, all should work. And STA has to take that into account and be pessimistic. How STA does that is slightly advanced topic, but we should be aware at the conceptual level that there can be variations which can happen, and that STA takes that into account. Okay. You can have variation within a die itself, as in within this die, different parts depending upon manufacturing. There can be manufacturing defects also. Their delays here and here can be different, and STA also takes that into account. So it's important to understand that because of manufacturing process, there can be variation, and STA takes that variation into account. There can be variation between two different wafers. Within a chip itself, there can be variation, and some of these aspects are covered by STA. There is also another thing which is done is you have typically logical libraries to cater to this, there will be logical libraries with minimum delay values, maximum delay values, and nominal values. And STA takes all these libraries, and for example, if it has to use maximum delay for a path, it will take from the maximum library, and it has to use minimum delay from the path, it will use minimum. So those things are known as modes. So there can be process variation and modes which STA needs to take into account for doing a thorough timing analysis. So let's start with clock specification, how clocks are specified in timing constraints. Clocks are specified using the command called create clock. Create clock specifies a primary source, typically on PLL or on some other design input ports of the design, as using the create clock command. There are multiple options to the create clock command. So you specify create clock, you specify what is the period of the clock, and for example, this is the clock, this is the period of the clock. You specify what is the waveform on the clock. Waveform means in the period of 10 units, when the clock is rising, so t equal to 2 it rises, and t equal to 4 it falls. So in a period, you define when the clocks are going to rise and when are the clocks going to fall. Then you attach the clock to certain design objects. For example, in this case, you are saying this clock should be created on this port, which is CK, or this net, C1, and you're creating the same clock on both of these nets. In addition to that, there is a name option where you're telling what is the name of the clock. Let's say I call this ACLK, and that is the name of the clock. So for a clock, you define period, you define waveform, and you're defining where you are creating these clocks. Some of these options are not mandatory. Waveform option is not mandatory. And what happens when you don't specify that option? We'll go and tell you. The object is not mandatory. That means you don't need to attach a clock to any design object. In that case, the clock is known as a virtual clock, where you don't have any design object. It's a virtual clock. It does not attach to any design object in the design. You can have more than 2 values in the waveform. So you are defining in a clock period time, let's say this 20 nanosecond, how the clock is going to change. And if the clock pulse is going within a period going to come more than once, you can also define that. What this means is clock rises at t equal to 2, it falls at t equal to 4, then rises again at t equal to 12, and falls at t equal to 14. And this is the behavior which happens. Now, all throughout the time, this same behavior is going to repeat. So clock is a periodic behavior. So this same behavior, every point of time, every 20 units is derived from library. So if library has default unit of nanosecond, this is assumed nanosecond, and this behavior is going to repeat. So waveform option can have more than 2 values as well. The only thing is waveform option has to define the behavior in a full clock period, which it is doing here, that within a full clock period, it is rising at 2, falling at 4, then rising at 12 again, and falling at 14. Because of this, the waveform should have even number of elements, because you're telling when the clock is rising, when the clock is falling, then rising again, and then falling. So rise and fall should be, for a periodicity, it should be even number of elements, and the same behavior then repeats every 20 units. What happens when the waveform option is not specified? So if, let's say, you define the clock with just period and define this clock on a design net or a port CK, then when the waveform option is not specified, clock is assumed to be 50% duty cycle. What is the meaning of 50% duty cycle? That rise and fall are of equal width, and rise happens at t equal to 0, and then fall happens at period of the clock divided by 2, which is 5 in this case. So if you don't specify waveform option, the clock, it's 50% duty cycle, and rise happens at t equal to 0, and falls happens at 50% of the period, which is t equal to 5 in this case. Create clock also has an option known as add switch, where basically which allows you to define more than one clock on the same net. For example, let's say you have this port in the design. You can define two clocks here, one with, let's say, 10 nanosecond period, another with 20 nanosecond period. But since you're defining the clock on the same port of the design, you'll be defining it in two commands, and you have to use an add switch, that you define one clock here and then used add switch to create another clock here, maybe different period or waveform, and define that. From design point of view, how this can happen is, let's say you have this IP, and IP is driven from a clock mux, and this clock mux actually is getting two clocks, one with 10 nanosecond, one with 20 nanosecond. In order to represent that when you're doing STA for IP, you would need to define two clocks so that your timing is done with both the clocks. And this is where -add switch comes to your rescue. Now let's understand how to define generated clocks. Generated clocks are clocks which are created inside the design. Typically, let's say maybe it's a divided version of a parent clock, or maybe multiplied version of a parent clock. And these commands which are used to define this is create generated clock. So create generated clock creates a version, either divided version, multiplied version, or some other modified version of a parent clock. This is defined using a command called create_generated_clock. You have divide by option, where you're dividing the frequency of the clock. So period actually gets multiplied. You also have multiply by option. One of those options can be used. Then the source, you are telling from which source this clock is created. So let's say there are two nets in the design, GC2 and GC1. Here you want to define generated clock, so you'll specify this option, and then you specify from where this clock is created, what is the source of this clock. And this source is a design object which you define using this -source option. What this creates is, this was your parent clock, and you have divided the frequency of this clock by 2. So this becomes your generated clock, and this generated clock is created on net GC1 and net GC2, which is a frequency divided version of your parent clock. So your period has become double. Your frequency has been divided by 2. You also have an option called master clock. What is the meaning of master clock? As we had seen, one net, which is the C1 net here, let's say has more than one clock, let's say CLK1, CLK2, CLK3. By what you're telling by master clock CLK1, that let's say if there are more than one clock on the source net C1, CLK1, CLK2, and CLK3, tool has to create a divided version of clock 1. So in using master clock option, you're telling with respect to which clock on the source you are creating a divided version. So you define source, you define master clock. It's important that there should be a path from source to the point in the design where you're creating the generated clock. Otherwise, STA tool will issue a warning that I cannot find the path. The path is important to find the latency or delay on the clock path from the source pin to where you are defining the clock. So I create generated clock, which you are doing on GC1 and GC2. has a source pin, and there should be a path from the source pin to the clock definition pin. Any point can be used as a source. Okay, you can use the clock pin here, pin here, pin here. Any point here, here, or here can be used as a source, as long as it is on the master clock reaches there, and there is it. The C1 need not be a create clock point. It can be any net on the path. In addition to using divide by or multiply by option, there is an option called edges, which can also be used. This is used to create slightly complex waveform which may not be 50% duty cycle. So let's understand how the edge option is used. So create generated clock hyphen edges. Edges will have odd number of elements, and these numbers indicate the master clock edges. So let's say you have this master clock or a source clock. This is edge number 1. Edge is when the clock changes. So you have edge number 1 here. Then edge number 2, so it rises here, falls here. This is edge number 2. This is edge number 3 of the master clock. Edge number 4, edge number 5, and so on. So with respect to these edges, using these edges, you are defining a generated clock where you are saying it rises at edge equal to 1. So it rises, generated clock rises at edge equal to 1. Then it falls at edge equal to 5. So 2, 3, 4, and 5 it falls. And then it rises again at edge equal to 7. So you have defined the clock here. This rises on edge 1, falls on edge 5, and then rises again on edge 7. So you've defined one periodic behavior, and this behavior then keeps on repeating. So with respect to the master clock or the parent clock edges, you are defined when the generated clock is going to rise, when it is going to fall, and when it is going to rise again, and that you have defined. So, and then the periodicity goes all throughout the time for the generated clock. So edges are usually used to define non-50% duty cycle, and these are the master clock edges used to define slightly complex clock waveforms of generated clocks. In addition to edge, you can also use an option called edge shift, which is always to be used. So edge and edge shift are always when you're using edge shift, you must be using edges option of the generated clock. And this can be typically used to generate pulses. Okay. So let's understand this example that you want to create a pulse like this. How do you define that in the timing constraint? So this is your master clock. And what you are saying is generated clock edges, the rise edge comes at the first edge of the master clock. The fall edge also comes at the first edge itself. And then the next rise edge comes at the third edge. So what you're saying is rise edge comes here, fall edge also comes here, and then next rise edge comes here. And then you're using edge shift option to shift these generated clock edges. So you shift edges, first edge, this one, by 0. Shifting the first edge by 0 nanosecond. These are time units. Second edge by 2 nanosecond. And the third edge by 0 nanosecond. So you created rise at first. Then you didn't change anything. You didn't delay it. Then the fall edge, it was 1, but you delayed it by 2 nanosecond. And this became the fall edge. Then the third rise edge is this, and you didn't delay it. So this became your clock pulse. So you define edges option. By edges option, you're saying rise happens at edge 1, fall also happens at edge 1, and then the next rise happens at third edge. You shifted the rise edge by 0 nanosecond. So it stayed here. You shifted the second edge fall edge by 2 nanoseconds, so it became this, and you shifted the third edge by 0, and it became this. So you created this fall. So you're using edges and edge shift option to create pulses, typically how this is used. The generated clock, if you have a generated clock, it can have multiple paths from the master clock to the generated clock. And whatever is the worst path, even you're doing setup or hold, the worst can be max delay or min delay. The worst path is used to do timing analysis. Sometimes you need actually not all kind of paths. The paths can be sequential from the master clock to the generated clock. The paths can be combinational from master clock to the generated clock. And sometimes from design point of view or from functionality point of view, the right path is only combinational path. For example, let's say you have a clock divider here, and you're defining a new clock, which is divide by 1 version. So for divide by 1 version, the clock cannot take sequential path. It should only take combinational path. But STA does not by default assume that because it's pessimistic. There is an additional option to the generated clock called combinational. In lowercase, I'm using just to write caps. So when this option is used, the sequential path is not used for calculating the clock latency. Only the combinational path is used. And this is the option you can use to enforce STA tool to only use combinational path for latency calculation between source pin to the generated clock pin for delay or latency calculation. So combinational option is used to enforce STA tool to only use combinational delay. Clock groups command is used to tell STA tool between what clocks you have to meet timing and between what clocks you don't have to meet timing. Sometimes it may not be relevant to meet timing between all clocks. Before we go into that, let's understand basics that what are synchronous clocks and asynchronous clocks. Synchronous clocks are clocks where clock events happen at a fixed phase relationship. So basically, between synchronous clocks, edges are deterministic. If you know this edge is going to come at t equal to 0, you know when the edge of the next clock is going to come, and that is those clocks are synchronous clock. That events happen as a fixed phase relationship. They need not be same frequency. One clock can be divided version of another, but basically the edges relationship is deterministic or a fixed phase. For asynchronous clocks, there is no fixed phase relationship. These clocks edges are unrelated. They can come at any amount of time. Even though clock frequencies are same, if they're generated from different PLLs, the asynchronous clocks edges cannot be determined the relative mean. Now, STA focuses on synchronous clocks. That STA can only time paths between synchronous clock. Between asynchronous clock, STA cannot do any analysis or time path. For asynchronous clock, there are a separate set of tools, which are clock domain crossing analysis tools, which are used, but STA domain or region is synchronous clocks. There are additional set of clocks which are known as logically exclusive clocks. So let's say you have this mux in the design. Based upon the select logic, when select is 0, C1 will be selected. When select is 1, C2 will be selected. Both clocks cannot be selected at the same point of time, and because of the logical condition which is given by select, so these clocks are known as logically exclusive clocks. So if you tell STA tool these clocks are logically exclusive, STA tool will not time the paths between those clocks because it understands only one clock will be selected, and these are known as logically exclusive clocks. There is another set of clocks known as physically exclusive, which means that those clocks cannot be present together in the design. So let's say you have this marks, and here two clocks are created, GC1 and GC2, two generated clocks are created. Now at any point of time, excuse me, either the GC in real silicon, either GC1 will be present or GC2 will be present. Same net cannot have both more than one clock. So these clocks are physically exclusive because physically only one clock is present. If you tell STA that these clocks are physically exclusive, it will not time path between these two. What is the difference then between saying something to be logically exclusive or physically exclusive? Logically exclusive means that clocks can exist together, just that the selection is different. Physically exclusive cannot be present together. So if you have two clocks, X and Y, if they're physically exclusive, only one will be present. Since both cannot be present at the same time, there is no possibility of crosstalk between those two clocks, because when one is present, other won't be present. So physically exclusive will not have any crosstalk. If the clocks were logically exclusive, the crosstalk will be there. So it impacts when you do crosstalk calculation. But from timing point of view, timing checks won't be done between those two clocks. Logically exclusive clock can have crosstalk, physically exclusive cannot have crosstalk. So how do you define certain clocks to be asynchronous, logically exclusive, and physically exclusive? By default, if you don't say anything, ST assumes clocks to be synchronous. So if you just define two clocks using create clock command, create generate clock command, whatever the command is, if you don't say anything about those clocks, by default, those clocks are synchronous in STA. If you want to change the default behavior, which is being assumed as synchronous, use set clock group command. So you use set clock group command. You can tell clocks, I want to change the behavior to asynchronous. You can also use logically exclusive or physically exclusive. These only one option can be used. Now and then you use something called group option. You can have one or more group. Here, I have an example where two group options are used. It can be 3, 4, it can be any number, or one also, but at least one should be there. Now, when you specify groups, here I'm specifying one group here, another group here. What this means is there is no relationship implied between the clocks present in the same group. So there is no relationship implied between clock 1, clock 2, and clock 3. This command within a group does not imply any relationship. The only relation which is implied is across the groups. And what this command is saying, because I am using asynchronous option, that clocks in this group are asynchronous to clocks in second group. So that means clock 1 is asynchronous to clock 4, clock 5, and clock 6. Clock 2 is asynchronous to clock 4, clock 5, and clock 6. Clock 3 is asynchronous to clock 4, clock 5, and clock 6. But no relationship is implied between clock 1, clock 2, and clock 3. Similarly, no relationship is assumed or implied by this command by clock 4, clock 5, and clock 6. If you only have this command in your constraints, then the clock 1, clock 2, clock 3 will be synchronous. But that is not because of this command. This is because by default, clocks are synchronous to each other in STA. But set clock group changes the default behavior. Very, very important to remember that the group option, no relationship is implied between these clocks. Relationship is only being told or to the STA tool across groups. So that means clock 1, clock 2, clock 3, based upon this command only, there is no relationship which is implied between these two. They can be synchronous or asynchronous based upon other commands or what is the default behavior of STA. But this command does not tell what is the relationship between clock 1, clock 2, and clock 3. This command tells that clock 1 is asynchronous to clock 4, clock 5, and clock 6. Clock 2 is asynchronous to clock 4, clock 5, and clock 6. And clock 3 is asynchronous to clock 4, clock 5, and clock 6. What happens when only one group is specified? you have an option to specify only one group. In this case, again, within the group, there is no relationship which is implied between clock 1, clock 2, and clock 3. But when you specify only one group, there is an exception to the rule that what is followed. What this means is it's a special case that when you only specify one group, this means these clocks are async to all the other clocks in the design. So clock 1, clock 2, clock 3 are asynchronous to all the other clocks in the design. So let's say you have 6 clocks in the design. Clock 1, 2, clock 6. What this command means is clock 1 is async to clock 5, all clocks except clock 1, clock 2, clock 3, which is clock 5, clock 6, and clock 4. So this command, when you only use one group option, it means these set of clocks are async to all the other clocks in the design. So clock 1 is async to clock 5, clock 1 is async to clock 6, clock 1 is async to clock 4. Similarly, clock 2 is async to clock 5, clock 6, and clock 4. Similarly, clock 3 is async to clock 5, clock 6, and clock 4. Again, no relationship is implied between clock 1, clock 2, and clock 3. It only implies a relationship between clock 1, clock 2, clock 3, and other group is all clocks except clock 1, clock 2, and clock 3. Now let us go to next set of commands which are used to define clock characteristics or clock properties. What are multiple clock properties? You can tell what is the transition time of the clock, which is basically how much time clock takes to go from 0 to 1 or 1 to 0. That is known as clock transition time. You can specify clock uncertainty, which is for clock skew and clock jitter. So you can tell what is the jitter on the clock. The jitter as we had seen, clock period is not idealistic. The edge can come slightly before or slightly later than the ideal time, and that can be specified using the set clock uncertainty command, and it is known as jitter. Or you can tell the skew between two clocks, that if the clocks are on different paths between the same clock, between launch and capture, what can be the maximum and minimum skew, or between two clocks. Let's say you have clock 1 and clock 2 here. You can tell what is the uncertainty or skew between these two clocks. You can tell what is the latency on the clock path, and latency has two elements, source latency and network latency. So let's say you're defining a clock here and the source is here. What is my source latency? What is my network latency? And you can specify min and max value of that. You can specify sense of the clock, that whether clock is stopping at a particular point, or whether the clock sense is positive unit or negative unit. You can also specify those values. So you can specify using a set clock sense command that, let's say if you have a mux in the design, two clocks are coming here, C1 and C2, and I want C2 to stop here on mux B pin. You can specify it using the set clock sense stop propagation command. Or let's say you have an XOR gate and clock is coming as an input. Now at the output of the clock, whether the clock is going to rise when C1 is rising or fall when C1 is rising, tool cannot automatically figure it out because it's a non-unit cell, as we had seen earlier. So you can tell the tool that here the sense is positive unit or negative unit with respect to the input. So when the input is going to rise, the output is also going to rise. That means it's positive unit. You can specify using set clock sense positive. Or when input is going to rise and output is going to fall, you can tell by negative option using set clock sense command. Let's understand the next topic, port delays and boundary constraints. So port delays can be defined using commands set input delay, or set output delay. What is the meaning of these commands? So let's say you have an IP. Let's say there will be flop, which will be connected to input or output. Now, in order to do setup and hold timing, you need to meet timing even on these paths, which are from input port to the flop, or from output port, from flop to the output port. Now, in order to meet this timing, you need to know what is the delay on this path. But since this is not a flop, you also need to know when this is connected, what will be the delay on the outside of this design. And on the output side, what will be the delay here on this path. These delays are specified using input delay and output delay command. So you define this delay, what is the outside on the outside logic of this design using set input delay command, and delay on the output port on the outside of the logic using set output delay command. Now this delay can be dependent upon set input delay has you specify the delay value, let's say 10. You also specify the delay value with respect to a clock. There is a clock option as well, because delay can be dependent upon what clock is feeding this data. You can have more than one flop feeding as well. And this, let's say, C1 and C2. Now, when C2 is feeding this data, delay can be different. And when C1 is feeding, the delay can be different. So set input delay and set output delay commands provide you a clock option as well to define the delay with respect to a clock. If you have more than one delay because the clocks are different, you have to use an option called add underscore delay. So similar to create clock, when you had to define more than one clock, you had to use add option. You use add delay option to define more than one delay on a port. You has min option and max option to define what is the minimum delay, what is the maximum delay, because it's a range. And depending upon that, whether it's doing setup analysis or hold analysis, it will use appropriate delay. In addition to port delays, there are additional boundary constraints also. Not only you need to know the delays, there are other conditions also you need to know on the boundary, and those are specified by additional boundary constraints, like what is the transition on the input, that how fast or how slow input is rising. This can be specified by multiple methods. One is you can specify the drive, so which is basically nothing what you're specifying the resistance value here. And based upon that, how fast or slow the input is rising can be calculated by the STA tool. Or you can tell the set driving cell command, which basically is telling the STA tool what kind of cell is driving this input. And based upon this cell's logical library information, what is the transition time, tool can calculate what is the transition time here. Or you can directly specify set input transition, directly specifying what is the transition value here. So basically at the boundary, you are specifying how fast or slow or input is transitioning, because that then will be used to calculate inside the design what are the delay values. And this you can specify the boundary constraint using this set drive, set driving cell, or set input transition command. On the output side also, tool needs to know what is the load on the output. This can also be specified by multiple commands, and usually one command is picked to specify it. You can specify set port fan out number. So basically now what are the number of pins in the fan out, and an approximation of load of one pin is done in STA, and based upon that it can identify what is the output load. Or you can specify load in terms of multiples of buffer. For example, the load, you can specify the fan out load on this is, let's say, 5 times a particular buffer. Or you can specify the load in terms of capacitance value, and these are then used by the tool to calculate transition times on the output port, and whether those are meeting the thresholds or not. So these additional boundary constraints are typically specified automatically in the most of the STA flows, or you can use one of the constraints to specify this. Now, one important question which comes up is with respect to clock. So you remember for clock, we have set clock transition command. And for inputs, we also have set input transition command. So which command should be used then? What is recommended is if the clock tree or CTS is not, clock tree structure is not built, which short form of which is CTS, then you use clock transition command. And basically you're telling the tool that this is the transition value, minimum value or maximum value you should be using on all of the clock tree. Once the clock tree is built, you just specify the transition on input and let the tool calculate and use computed values. So if the CTS is built, clock tree is built, post CTS stage, use set input transition command just on the input and let the STA tool calculate the delay and use computed values. But if it's pre-CTS, clock tree is not built, then you use set clock transition command to specify the transition on clock period rather than making the tool calculate it. So far, we have talked about that most of the timing checks are done one cycle or between every pair of flop, timing checks are done. There is a particular important set of commands in STA known as timing exceptions. This can modify the default behavior. And let's understand how these timing exceptions, what these timing exception commands are and how they modify the behavior. Before we understand timing exceptions, we need to understand a format in SDC commands or constraint commands known as path specification. As we know, what are start points, what are endpoints in the design, and there is combinational logic between start point and endpoints. So there are multiple paths which can exist. And let's say you want to change a default behavior of these timing analysis on the paths. You should be able to specify on what paths you are changing the behavior. And to specify these paths, there are path specification which you need to do. And that path specification typically is done in any of the timing exception commands using 3 options. I'm writing in uppercase, but these are lowercase in actual commands. The options are from, to, and through. So what are these options? From, to, and through. From is used for the start points. And start points are what? Either ports or typically clock pin of the flops in the design. To option is typically used for endpoints. So from is typically used for start points. Through is used for endpoints. To is used for endpoints. And through is used for nets or nodes from which are combinational nodes, which are between the path from the start point to endpoint. And using these options, you can specify one or more paths to which you want to change the default behavior. So let's understand. Let's try to specify some of these options. Okay. So let's pick up a path here in the design. Let's say we want to do something on a particular path. Let's say this path here, starting from F1, going to here and here. So this is one particular path. Now, in order to specify this path, we'll say the from option is F1CK because the path, that is the start point. So it is F1CK. This is where the path starts. It goes through U1A and then U1Z, and then it goes to F5D. So using these options, hyphen from, through F1CK, hyphen through U1A, hyphen through U1Z hyphen 2 F5D. You have specified the path here, marked by this red. We have specified this particular path. Now, this is the path specification. If you just use one of the options, let's say you just say F1CK, here you just say from F1CK, then it can apply to more than one path. What paths it can apply to? All the paths starting from F1CK. So there is this path which is starting from F1CK. There is this another path which is starting from F1CK. There is another path which is starting from F1CK. So you can use, if you use just one of the options or a little bit lesser option, in general, it can apply to more than one path as well. For example, let's say you just use through U1Z. That means all the paths going through this, it should apply to. So it will apply to this path. It will apply to this path. It will also apply to this path. Right? Or if you just say, let's say through U3O, which is here, so it will apply to this path. It will also apply to this path. Okay, so this is how path specification options are used. From and to option can only be used once, but the through option can be used more than once to guide the path accurately. Okay, like in this case, the path drawn in red, to draw it more, to guide it more, STA tool more accurately, you will use F1CK, F5D, hyphen through U1A, and one more through U1Z. The through options are ordered. What is the meaning of that is, if you use F5D and use, let's say, through U1A through, and it's ordered how to write the command U1Z. So that means path has to first go through U1A and then U1Z. So it goes through U1A and then goes to U1Z. But if you use U1Z, then hyphen through U1A, it will not apply to any path because there is no path which first goes through Z and then goes through A. The path is on the opposite direction. So through options are ordered options and you have to use it accordingly. Now let's understand what are the various timing commands which use exception commands which use this path specification and basically change the default one cycle or zero setup and zero cycle hold behavior. The first command is set false path command. What set false path command tells the STA tool is don't time these paths. So for example, coming back to our option, hyphen from, hyphen through, hyphen to, let's say we say from F1CK through U1Z to F5D, whatever path is specified using this, don't time that path. So let's see what is the path specified with this. From F1CK, this means this, U1Z to D. You are telling STA tool, don't time this path. If you use just few of the options, as we know, it will apply to more than one path. There, it may be you're telling the tool to not time more than one path. So if I just say from set false path from F1CK, that means don't time any path from F1CK, and there can be more than one path. One path is this. One path is this. Another path is this. So you're telling the tool, don't time any path from F1CK. Path specification can have, rather than just using one value, you can use a list. Here you can say F1CK and F2CK. This means don't time any path from F1CK and also F2CK. So basically you expand those options when ST tool expands the third option when calculating it. You can also use, similarly, you can use list in the other options as well. So from F1CK, F2CK to F4D, F5T. What this means is you will do all expansion. This means from F1CK to F4D, no timing should be done. From F1CK to F5D, no timing check should be done. From F2CK to F4D, no timing check should be done. From F2CK to F4D, no timing check should be done. So this is how specify. False path means you don't want to do any timing check. Set multi-cycle path is used to change the default behavior, which is one cycle. So let's say you have this path, and this is very slow logic, and you don't want to meet, you cannot meet timing, you don't want to meet timing in one path, and you have appropriately added an enable condition so that the path takes 2 cycles. Here, you can, rather than telling it, you can tell STA tool, don't meet this path timing in one cycle, but do a cycle timing of setup for 2. So FF1 to FF2, you don't meet timing in one cycle, but you meet in 2 cycles. So default timing relationship was that you're launching data here and you're capturing data here. With using this setup multi-cycle path of cycle 2, the check has shifted by 1 cycle. And now tool is doing a 2 cycle because it has shifted by 1 cycle. So now the shift is shifted by 1 cycle and you're meeting timing, checking timing in 2 cycles. So rather than default setup, now tool is checking when you're launching data here, it is not captured, it cannot be captured in 2 cycles. So this has changed your modified setup timing check because of this multi-cycle path command. When you modify the setup check, hold check is also modified automatically. Why hold check is modified? If you remember our hold checking rules, that data launched at current edge should not be captured in the previous edge, and data launched by the next launch edge should not be captured by current capture edge. If your launch and capture edges are changing because of this relationship, your hold relationship is setup relationship is modified, but hold relation, because it is dependent upon setup, is automatically modified. If you don't want to modify the hold relationship and you want to return it to default, then typically you will add a hold multi-cycle path command also with setup. And typically these commands, unless specific cases, these commands are used in pair. Here, what you are saying is, I modified the setup relationship to 2 cycles, which modified my hold relationship to this edge, and I'm reverting it back to and correcting it by using this command to 0 cycle hold. Okay. So basic thing is, when you modify the setup timing relationship, hold relationship is automatically modified, and to bring it back to its original value, typically you specify a multi-cycle path with setup -1 hold value. This brings hold to default 0 cycle check. So when you want to modify the timing relationship in number of cycles, you use set multi-cycle path command. If you don't want to do timing check at all, you use set false path command. If you want to modify the timing check to specific delay values, which could not be done by multi-cycle path command, use set max and set mean delay values. Set max delay value sets a maximum delay value on a path. So basically what you're saying is, on this path, this is the maximum delay which can be there, which is kind of doing a setup check with this particular delay value. And this is the minimum delay which can be there, which is kind of doing a hold check with this delay value. And that you can specify using set mix delay and set min delay command. Set disable timing is typically used to disable certain timing, and typically it is used for certain cells. For example, let's say you have AND gate, and there are two inputs of the AND gate, A and B, and output is Z. And you want to disable certain arcs, maybe it's a useless arc in the library, or for whatever reason, you can tell the tool, disable the timing from pin A to pin B, Z. And then tool will not use that value for delay calculation, or if this is part of some path, that path won't be timed, or this delay value will not be. So it will basically, this arc which exists, it will cut that arc, and it will not be used any in delay calculation or calculating any path. What should you use? As in, you have one set false path command for not timing paths, and what is set disable timing, also for making certain paths to be not timed. Set disable timing is typically used for cells to disable certain arcs. Set false path is used to say don't meet timing on these paths. So typically set disable timing is used for arcs. Although you can also make path false using set false path. For example, if you disable this arc, the path between these two flops will not. But typically, as a good principle, set disable timing should be used for disabling the arcs. Set false path should be making to make the path false and not meet timing. Set false path is more robust. That, for example, let's say there are two clocks here coming here, C1 and C2, and there are two clocks here, C3 and C4. Set disable timing will just not time any of the paths. Set false path command can be used to all false specific paths. You can tell the set false path command only set false path from C1 clock through this flop to this pin and C3 clock. But C2 to C4 will still be timed. You can specify that using set false path command. Set disable timing does not have those options. So it's typically, as a rule of thumb or as a good principle, should be used to disable the arc, while set false path is more robust, can be used to false path only specific paths between a pair of start point and end point. You can select which clocks as well. Now let us go to last set of commands, which is used to define multiple modes in SDC. So there is a particular command in SDC known as set case analysis command. Set case analysis command is used to specify a certain portion of the design and specify a constant value. That net may or may not be constant value in the net list, but you can override that using a set case analysis command. For example, let's say you have a mux in the design, and then there is a select on the mux, and there is a test clock coming to this mux, and there is a functional clock which is coming to this mux. And let's say you want to do analysis only in functional mode, so that only functional clock should propagate. How you can do that? Using set case analysis command. So on this select line, you can apply a set case analysis command and tell this select is 1. So you can say set case analysis 1 on select. You have not connected select to 1 in netlist. You've just added a constraint command that set case analysis 1 on this select. Now tool will assume, STA tool will assume that this select is 1, and because of that, test clock will not propagate and only F clock will propagate. So this can be used to do specific mode selection or specific certain nets to be set to a constant value, which may or may not be constant in the net list. For example, let's say you have an IP, it is used in multiple chips. So you don't want to connect a net to a constant, but you want to do analysis when this particular net is at a constant value. You can do it using this set case analysis command. So that covers our SDC portion of the design as well. Thank you for attending this webinar. If any of your questions was not answered, you can go to our community, register, and type your questions to community.vlsideepdive.com. It may be questions related to this particular webinar or any other questions you may be how to find jobs, how to write resume. You can post any question. It's a community for VLSI engineers. And our experts and other members in the community will help you there. You can follow our LinkedIn page. So just search for VLSI Deep Dive and you will find our page. And you can follow our page to get to know more updates, to get to know what new courses we are launching, and general things which we are posting. This is our website, www.vlsideepdive.com. If you need any other support, any questions, payment for a course, or if you run into any issue, just drop an email to us at support@vlsideepdive.com. We'll soon be launching an advanced course in STA. This will also have labs. So follow our LinkedIn page, stay tuned, and you'll get to know the information about when that STA advanced course is launched.